She's a professor in arithmetic geometry at the Technical University of Munich. She studied at the University of Bonn, where he got a PhD in 2005. The title was on affine Lusztig varieties for GLN, and was supervised by Michael Rapoport. This thesis won the Felix Ausdorf Memorial Award. She earned her habilitation in 2010, and in 2012 was appointed to her professorship at the Technical University of Munich. The title is Moduli Spaces of Local G-shtukas.
Yes, thank you very much, and it's a great pleasure to speak here. So, moduli spaces of local G-shtukas. Before I even explain what this is, let me summarize very briefly the more classical or more developed arithmetic case. These moduli spaces were first studied in a very particular case by Drinfeld in the 70s, and then later in the 90s, this field got a new impetus by the great generalization, by the definition of moduli spaces of p-divisible groups by Rapoport and Zink. For example, they proved uniformization of Shimura varieties along Newton strata using these moduli spaces, and they constructed these moduli spaces in the situation where they parameterized p-divisible groups together with an EL or PL structure. That means they have additional fixed endomorphisms and a level structure, or in addition, polarization. So from that point on, a large number of people worked in that area and studied these moduli spaces, described their cohomology, studied their geometry, and so on. So I don't want to summarize the whole theory, and instead just mention two, or the generalizations of the construction itself. So on the one hand, there were generalizations to other groups, for example, to additional structure and moduli spaces of p-divisible groups of Hodge type and of abelian type. These were, as Rapoport and Zink's original construction, formal schemes. And if one restricts attention to the generic fiber, then there's the concept of local Shimura varieties, which is even more general and works for all groups. And this was conjectured by Rapoport and myself, and then later proved by Scholze. He also talked about this today. So this is the arithmetic case, and today I don't want to talk about this very much, and instead outline the parallel theory for local functions fields. So if I want to summarize it in one line, I want to replace the rational numbers by the quotient field of the polynomial ring over fp in a variable t, and correspondingly the p-adic numbers, p-adic rational numbers by the Laurent series over fp and t, and the and zp by the power series ring over fp. But of course, now you have to ask, what are the analogs of p-divisible groups? What are the analogs of the moduli spaces? And this is what I want to explain. So the first part of my talk will be to explain what moduli spaces of local G-shtukas are. And then in the second part, I will summarize what, at least some part of the state of the art in this field is. So in order to introduce even local shtukas, not yet moduli spaces, but local G-shtukas, I need some notation. So I fix a finite field, fq, and f is supposed to be its algebraic closure, and I fix a parahoric group scheme over the spectrum of fq in and power series in a variable z. The easiest example, and the example that I will refer to from time to time, will be the constant group GLN, or the group SLN. This group GLN would correspond to just moduli spaces of p-divisible group without any additional structure. So that's somehow a good first example. And with that, I associate a couple of loop groups. First, the group of positive loops associates with an FQ algebra R, the R of the valued points of the group G, and correspondingly the loop group itself, there you take R and then Laurent series in the valued points. And the flag variety is then the quotient. You have to make a bit, make sense of this, but very roughly it's just the quotient of LG modulo the group of positive loops. It's called affine flag variety associated with my group G. So as an example for GLN, this flag variety, it corresponds, or it parametrizes, if you take the f valued points, it parametrizes lattices in the n-dimensional vector space over the field f and then Laurent series in Z, where lattice means you take a free f power series in Z module of rank n. And each lattice can be obtained from the standard lattice by multiplication by anything in LG, and the automorphisms of the standard lattice f power series in Z to the n are just the positive loops. So this is the flag variety. Okay, so now let me explain what local G-shtukas are. They will live over base schemes, which are schemes over FQ in a variable Z, where Z is a zeta, which is now a different variable from what we had before. So zeta is to parameterize the variable in the base scheme, and Z will come up in a second again. Okay, so zeta is supposed to be locally nilpotent, and then I consider local G-shtukas as these are pairs consisting of an L plus G torsor over my base scheme, together with a Frobenius morphism. This is an isomorphism of the associated torsors for the full loop group. Okay, so, and as morphisms between them, I consider quasi-isogenies. These are, again, isomorphisms after inverting Z, so to say. So isomorphisms of the LG torsors that are compatible with the Frobenius morphisms in the sense, in this, this commuting condition on the right. Okay, so one example again for my example of GLN. We have an equivalence between L plus GLN torsors and OZ modules, which are Zariski locally free of rank R. And then we have, in the same way, an equivalence between local GLR shtukas and so-called shtukas of rank R. So the torsor corresponds here to this sheaf M, and the Frobenius morphism tau G then is translated into an isomorphism of the corresponding OS Laurent series in Z modules. So this is maybe a bit more explicit, this example. So I claim that this is my analog of p-divisible groups. So what is this analogy? So let's stick to this example here and consider, for example, the zinc display of a p-divisible group. So in the arithmetic case, we can consider a formal p-divisible group, so that display theory works over a ring R such that p is nilpotent, and then zinc associates with it a display that corresponds or consists of several conditions. Let me just name a few. You have a finitely generated projective W of R module. So this corresponds to my sheaf of OS of Z modules. And then you have here such a sigma linear epimorphism from a submodule Q to P. This corresponds to my phi M, but it's a little better than what I assumed. Namely, we have here a submodule. First of all, it's surjective, and it's defined on a submodule which is not too far from P itself. It lies between P and IRP, where IR is the vanishing of the first, where IR is the image of Verschiebung. So in particular, Q is very close to P, and still you have such an epimorphism always. So to summarize this example, Local G-shtukas are more general than just the analog of p-divisible groups in two respects. First of all, we consider general groups G instead of just this example. And secondly, we don't have this condition that, this boundedness on the Frobenius homomorphism. The first thing is very good, that we can consider general groups as a nice feature. The second thing is not so good. We want boundedness conditions because otherwise, first of all, we don't have any analogy to p-divisible groups, and our moduli spaces will be, totally uncontrollable. So, how do we introduce similar bounds for local G-shtukas? The first idea is the following. We consider a local G-shtuka over such a base scheme S, and we want to trivialize it first to introduce these bounds. So we take an italic covering of S that trivializes the torsor here, and we also choose such a trivialization. And then the Frobenius morphism tau induces a morphism for this trivial L plus G or LG torsor. In other words, it's multiplication by an element of the loop group. So what you get from tau G is such a map from S prime to, the base change of the loop group to FQ of zeta. And you want to study this, or you want to bound the singularities of this morphism, but of course it depends on the trivialization. And so the first thing is you consider only its image in the flag variety because this corresponds to forgetting somehow the trivialization on one of the arguments. Then the second condition is that you want, you could also mod out L plus G on the left as well. I will talk about this in a second. Okay, so this is the morphism, and I want to bound this. So I consider for the beginning, I consider just any closed-in subscheme of my flag variety for some finite extension R of FQ of zeta. And I say, my local G-shtuka is bounded by the subscheme if for every such trivialization, the corresponding map that I just explained is factors through my subscheme. This is somehow the ansatz that I want to make for the bounds. Now, of course, the question is, which subschemes do we want? Definitely not everything. Let me give one example, again, for one of my favorite very simple groups that were too simple for the last talk, but are just right for mine, for SLR. So here the flag variety in a very similar way as for GLN can be described explicitly. So here we have first our locally free OS of Z module of rank R corresponding to my torsor. And then the second condition, this alpha, this means triviality of the determinant, essentially. So that's the determinant condition. And again, we have a Frobenius morphism. This trivialization here corresponds because I consider the flag variety, and I want that everything is that this delta and alpha are compatible, but I skip this compatibility condition. Okay, and I consider the following example of a bound, of a subscheme of my flag variety. So I fix R, this is just the power series in zeta over FQ, and I fix a number n that determines my bound, so the bound gets bigger and bigger the larger n is, and I want to bound the singularities of this morphism delta here. So I consider here the image of delta, and not only the image of delta itself, but also its exterior powers. And, I just want that it's contained in some, shift of the standard lattice, or the exterior power of the standard lattice, by some power of z minus zeta. And, these powers are here a multiple of j squared minus jr, where j is the exponent for this exterior power. Why is this reasonable? The first thing is, if you do it like this, then this compatibility with alpha automatically gives the condition for j equal to r for the highest exterior power. You just get, again, compatibility with alpha, and compatibility with alpha even gives you equality for j equal to r. You could, in this same way, also define other bounds. So you could also replace the other exponents that you have here by something different. Yeah, as long as they are all finite, you can determine in this way many bounds. And via representations of other groups, or you could also do the same for, or similar things for GLN, and via representations, we can give examples of bounds for more general groups. So this gives me a class of bounds, and all of these are bounds that I actually can consider later on in the theory. So they will satisfy all the conditions that are needed for bounds for local G-shtukas. And then, so what are actually bounds? If one not only wants to give explicit examples, there's one way to approach this question on bounds, but rather asks what is the minimal requirement that I want for bounds. Then one can start with a list. I want a closed-in subscheme of the flag variety, and up to equivalence. That means essentially that I want to be able to change this R here. And I have a number of conditions. Well, R, as before, is a finite extension of valuation rings. And then I want that Z hat is stable under the left L plus G action. This first condition essentially comes from the fact that this bound was obtained, or this map that is supposed to factor through the bound is obtained by trivializing the local G-shtuka. And if I change the trivialization, I will get a different image, which differs by something which is it differs by the L plus G action. So if I want to have some well-defined condition, I need this invariance. Then I want a zeta-adic formal scheme with quasi-compact special fiber. That's a finiteness condition that is certainly necessary. There's this third condition, fourth condition. I want that there is a relation to the examples that I just explained, in the sense that there should be a faithful representation of my group over FQZ, and some n such that under this representation, my bound factors through one of the bounds that I just explained. The reason for that is that later on we want to construct moduli bases and take their generic fibers, and this condition here ensures that we can do that. And there's essentially one more condition saying that the generic fiber is also invariant under some sort of left L plus G action, and then if one wants to be rigorous, one has to explain what this equivalence means. So this is a set of conditions that we actually need for bounds, and now one could, of course, ask what other important examples there are. In any case, these are the bounds that I want, and for any such bound, I consider associated with them also, in addition to this ring R over which that hat is defined, I consider also a ring R breve, which is, as usual, the completion of the maximal unramified extension of R. The quotient field of R is called E. This should remind you of the reflex field in the arithmetic case, and E breve is the quotient field of R breve. Okay, so then we are ready to define our moduli spaces of local G-shtukas. What we need is one fixed local G-shtuka over F. This fixes, so to say, in the arithmetic case, the isogeny class of the p-divisible group. And here we are also mainly interested in the isogeny class of this local G-shtuka, and we need a bound. And now we make essentially the same definition as in the arithmetic case. So we want to parameterize local G-shtukas over S, which are bounded. And notice we have here this little inverse. Okay, I didn't explain what the inverse of a bound is. What you should think of is we bound the inverse of the Frobenius by Z hat. this is actually equivalent to what we have here. And we do that later on because at some other point signs cancel then. So we take the moduli space parameterizing local G-shtukas over S, bounded by our the inverse of the given bound, plus we require that they are quasi-isogenous to the base change of our fixed local G-shtuka, and we fix such a quasi-isogeny, and the whole thing up to isomorphism. So this is really the analog of Rappaport-Zink moduli spaces. This bound occurs automatically for p-divisible groups. And, well, as in the arithmetic case, these moduli spaces are int-representable by a formal scheme over the formal spectrum of this ring R-private, which is locally formally of finite type and separated, so very similar to what we are used to. This was first shown for split groups and a particular class of bounds by Hartl and myself, and then later generalized by, in the thesis of Aras Terad, a student of Hartl. And these spaces are then called Rappaport-Zink spaces for bounded local shtukas, or moduli spaces of local G-shtukas. So these are the objects of my talk. Good. So what properties do they have? Well, first of all, what one expects is that they have just the same properties as in the arithmetic case. And if we directly compare the definition, we see that the definition is very analogous, but we can just write it down without any effort for general groups. And we have here bounds which are more general than the bounds that we had before. So if this n in my example of a bound is not equal to 1 or so, or even none, the bounds not necessarily correspond to minuscule co-weights. So we have here really a more general situation than considered by Rappaport and Zink. But apart from that, for example, on Rappaport-Zink spaces, you have this action, natural action of the quasi-isogeny group, and of course you have this here as well. You have the group of self-quasi-isogenies of the local G-shtuka defining the whole moduli space, and then this acts by composition with the isogenies. And, well, if you trivialize this defining local G-shtuka, you can write it as L plus G over your FP bar, algebraic closure of FP, and then Frobenius is given by some element in LG of F. And then this quasi-isogeny group is just this well-known group JB of FQ of Z, the group of elements sigma commuting with this element B defining the Frobenius. And also, you consider again the generic fiber of the Rappaport-Zink space, M breve an. This is the strictly E breve analytic space. So for this talk, I want to consider Berkovich spaces. Of course, you could also do differently, but we chose it to be like this. And generalizing the p-divisible group case, you can trivialize the rational dual Tate module of the universal local G-shtuka, so there's also such a notion in this case here, and obtain a tower of coverings of the generic fiber of the moduli space. So all of this is fairly analogous to what we are used to. So this ends my first part of the talk. In the second part, I want to summarize some of the main results that we know. I want to study the special fiber and the generic fiber and relations to global G-shtukas. So what do we know about the special fiber? If we want to study the special fiber, so for zeta equal to 0 of these moduli spaces, then first of all, we are interested in the special fiber of our bound, or of the inverse of the bound. And we can describe the set of points of the special fiber of the moduli space by an affine Deligne-Lusztig variety. So we fix, to define affine Deligne-Lusztig varieties, we fix an element B in the loop group, and we fix our Z inverse. This is, if we come from this moduli space, it's just the special fiber of our bound, but we can do this for any reduced closed-in subscheme of the flag variety. which is also left invariant under L plus of G. And then we can define the f-valued points of an affine Deligne-Lusztig variety as the set of all those G, such that if you sigma conjugate B by the element G, then it ends up being in this defining set Z inverse. So this is an affine Deligne-Lusztig variety in this general situation. And one can show then that this describes exactly the underlying reduced subscheme of the moduli space. This underlying reduced subscheme is a scheme locally of finite type, and it has projective irreducible components, and in fact, quite a bit is known about its geometry, well, as long as your group is not too complicated. So for example, if G, instead of being just any parahoric group scheme, is in fact a reductive group, then one can, for example, describe the connected components, the dimension, in many cases also the irreducible component, the set of irreducible components of these special fibers. There are also some partial results known in the Eva-Horry case, so if G is an Eva-Horry subgroup, or some results also in the general case. But I don't want to say too much about it. These properties are really studied by many people, and there's a whole theory about it. But, well, 2 talks later, we will have a talk by Shuhua He exactly on this. So I refer just to this talk for more on the special fiber of these moduli spaces. The next thing I want to talk about is relation to global G-shtukas. So what are global shtukas, or global G-shtukas rather? If you want to generalize this, you replace your FQ of zeta by a smooth projective, or FQ, yeah, by a smooth projective geometrically irreducible curve over FQ, and you consider again a parahoric group scheme now over C. Okay, and then you have global shtukas here. Or, well, I should say global G-shtukas, so there's a G missing here, with n legs over a scheme S. Well, it's a tuple where you have a G torso, again over C, base change to S, and then you have n point or n S-valued points where you might have singularities of your Frobenius, so you have these legs, Si, which are pairwise disjoint, and a Frobenius morphism outside of the graphs of these legs. So these are global shtukas, and there is also a moduli space of global G-shtukas. I don't want to go too much into detail. What I want to say is how to relate, or what the relations are to my moduli spaces of local G-shtukas. So what you have to do to relate them to local G-shtukas is you have to take the formal completion of this moduli stack of global G-shtukas in a point. So you take a point here. Well, it should be outside the diagonal, so Ci should be different from Cj for all I and j. And then you can complete this moduli space of global G-shtukas in this point of C to the n. And, well, this formal completion is what has a direct relation to moduli spaces of local G-shtukas. So you cannot directly relate the whole thing, but instead consider these formal completions. But then, let me just very briefly summarize. Then we have all the analogs of what we have in the arithmetic case. So there's an analog of the Serre-Tate theorem for deformations. There's an analog of Rappaport-Zink uniformization for Newton strata in these completions of the moduli space of global G-shtukas by moduli spaces of local G-shtukas. And there's also a product structure of Newton strata. So in the arithmetic case, there's this result by Mantovan writing Newton strata as a product of Rappaport-Zink spaces and Igusa varieties, and this also has an analog in this situation here. So these are the direct analogs of essentially all the relations to the global situation, or all the geometric relations that we have in the arithmetic case. So the last class of results that I want to explain to you concerns period maps, so is somehow a bit closer to what Peter Scholze talked about today. So we want to consider period domain, period spaces. And there is really a big difference between the Rappaport-Zink situation and our situation. And this big difference comes from the fact that we are considering more general bounds, so not only minuscule bounds. And this is why we cannot just consider Hodge filtrations, but instead have to consider something more general, which I call a Hodge-Pink structure. And in order to define it, I first consider the base change of my group here to the spectrum of FQ, Laurent series in zeta, and then power series in Z minus zeta, under, well, the natural map sending Z to itself. And what you notice here is that this Z in the image, well, it's a power series in Z minus zeta with a non-trivial constant coefficient, which is invertible in FQ of zeta. So Z becomes invertible. So this map factors through the generic fiber of my parahoric group scheme. So in particular, my new base changed group is now reductive. Okay, so I consider the analog, well, the same construction as for the flag variety I had before. Now it's called the Grassmannian because the group scheme is reductive. This is called the Biederam Grassmannian because, well, it is the direct analog of the Biederam Grassmannian in the arithmetic case. This is an projective int scheme. And now, what is the space of Hodge-Pink structures bounded by my bound? Well, I just write it down as being the base change of Z hat to I breve. Now, of course, you can very well ask, well, what has this to do with Hodge filtrations? Why is this called the space of Hodge-Pink structures? So let me make this a little bit more explicit. So this is my space of Hodge-Pink structures. I fix a faithful representation, or you could directly consider the group GLN, but for general groups, I fix a faithful representation with the representation space V, and then associated with my element B. This is the element describing my defining local G-shtuka that defines the moduli space. With that, I associate a Z isocrystal over F. Here's my defining local G-shtuka, and I define an isocrystal. Well, I tensor V to the algebraic closure of FQ, and the Frobenius morphism is just given by the image of B under my representation rho. And now in there, I consider a submodule. This is this Hodge-Pink structure. So for every element here in this Grassmannian, so this corresponds to an element up here. For every such element, and for L any extension of I breve, I consider a submodule of this isocrystal. This is a free submodule of full rank, QD of V. This should be a gamma instead of a V. Rho of gamma times V times somehow the standard lattice in here. This is a free submodule of full rank of my isocrystal. Okay, so in this way, I get a submodule, and this now resembles a bit more the Hodge filtration. Of course, it's more than just a filtration, but this is what I want anyway for my more general bounds. Okay, so now I have my space of Hodge-Pink structures, and now I want to explain what the period map is. And here again, the idea is to proceed as much as possible as in the arithmetic case. So in the arithmetic case, as well as here, the very rough and of course not correct, not strictly speaking correct idea is to consider first the inverse of the universal Frobenius over the moduli space. As the Frobenius is bounded by Z inverse, this inverse is now bounded by Z, so this is where the signs cancel. And then I use the universal quasi-isogeny to transport this somehow to a Hodge-Pink structure to such a submodule in the isocrystal corresponding to D. Well, of course, this is not really what one does because we want to work on the generic fibers, and there you cannot just consider the universal Frobenius, but as a very rough approximation, this is what you do. And so what you can then show, if you make this construction really precise and work, then this induces, as before, an étale morphism, the so-called period map, which has image in the so-called admissible locus in the analytic space associated with my space of Hodge-Pink structures. So here right on the right, you have your space of Hodge-Pink structures, the analytic space. And in there, you have the so-called admissible locus, and the period map factors through that and gives then an étale morphism to that. OK, so so far so good. What are the properties of this period map? So I just write them here as a bullet list, but in fact, this is the main theorem. The only point is that I will not explain all the notation in detail. So under an additional assumption, namely, I have to assume that the generic fiber of my group is unramified. Then we can describe the image of the period map. I would like to say it's just the same as in the arithmetic case. This is halfway true. The image of prévia can be described as a certain locus where two tensor functors coincide, which is a description that you also have in the arithmetic case. However, there you can go a step further. There's a theorem by Vantin-Berger identifying this locus with the locus with the so-called neutral admissible locus. So this is a union of connected components of the admissible locus that you can explicitly describe in terms of these elements B and gamma having the same image in the fundamental group. So there you have a very nice and explicit description. So this theorem of Vantin-Berger is something that is still missing in this function field case. So there's still, at this point, room for further results. But apart from that, so what of course is what we of course conjecture is that this should also hold in the function field case. And then one would like to define towers of coverings both on this admissible locus and on, and then one already has these towers on the moduli space, and one wants to identify these towers. And in fact, this is true. So we have a natural tensor functor from representations of G associating with such a representation a local system of FQ vector spaces on this admissible locus in this space of Hodge-Pink structures, or in this period space. And this natural tensor functor, this defines a tower of coverings associated with these local systems. And via this period map, these local, this tower of coverings is canonically identified with a tower trivializing the rational dual Tate module, so the tower over the Rappaport zinc space, including the Hecke action that one has on these two towers and the action of the quasi-isogeny group, self-quasi-isogeny group of the defining local G-shtuka. So also for these period maps, we have a very analogous theory. Okay, thank you very much.